So in this video, I am going over the problem of endogeneity in a regression function and the solution to that, which are called instrumental variables. So taking out a simple function here where x affects y with the given coefficient, ideally we want our beta to act as a causal effect, but realistically in the real world, there's usually another unobservable variable that affects both x and y, which means this beta right here doesn't directly affect y. This kind of problem is known what we call as the endogeneity, called the type of confounding effect, where the x variables and then the errors are not random. Note that this is when you recall the mandatory assumptions for the linear and multiple regression. This isn't necessarily a requirement. This is kind of a consequence for it. All right. So this is kind of hard to interpret. So we can kind of see examples of when this problem occurs. A change in y will affect a change in the covariance of x and y, called the causality bias. Omitted variable bias. We went over that in linear regression, but simply put, when we forget an important independent variable to include in the regression function, so we omit it by accident. When the covariance has a persistent measurement error, a non-random measurement error, and then when our y variable is lagged. So the fourth one, not the most common. I've never personally gone over that, but just kind of a summary of this. If this is intuitively hard to interpret, you can kind of generalize it as basically endogeneity, meaning saying that our function is simply just incorrect. That is a little general, but when we have problems of the omitted variable bias, and when we have like these confounding errors where x doesn't actually affect y, I don't think it's really a stretch to say endogeneity can be interpreted as our model is just far off from the ideal model. All right. So looking at the supply and demand example here, just like economic function where usually demand would impact supply, we can ask ourselves, well, what if supply actually affects demand more than demand affects supply, right? So that's kind of an example of endogeneity, kind of a Granger causality example I went over last video, but just one of the examples. And so our consequence for this is that we actually have a biased LS estimator in contrast to our unbiased LS estimators in our consequence for heteroscedasticity and autocorrelation. The autocorrelation and heteroscedasticity, those are unbiased because those consequences are based on our data set, while the problem of endogeneity is caused by our fitted model or our type of our regression function that we made. And that's why we call it biased, because it's simply just incorrect. And so in response to this, in addition to this, our standard errors are obviously still incorrect, and the sample size is irrelevant, including more is irrelevant because our function is incorrect, not necessarily that the data is unreliable. And you can see that now based on these consequences that endogeneity is a lot more punishing than heteroscedasticity or autocorrelation. All right, and so just like what I said in the beginning, the most common solution to this is what we call instrumental variables, denoted most commonly as VI. So visually, we can kind of see that we don't know if X affects Y based on these unobserved confounding effects. Then we include this Z variable to help us determine what affects what. So if our X variable is endogenous, has a problem of endogeneity, ideally we want to split that into two parts, which the two parts being the part that is correlated with the error, the part that makes it endogenous, and then the part that's not correlated, so the part that's exogenous or non-endogenous. So when we ask ourselves, what makes a good instrumental variable, we don't want a direct effect on Y because often that will result in an autocorrelation, not autocorrelation, but a correlation on the X variable. Sorry, that's not why. We want our X variables to be strongly correlated with the instrumental variable, but we don't want a direct effect on Y because our instruments are trying to help the independent variable and not necessarily the dependent variable. And we don't want any correlation with the error. So correlation with the error and then the new instrumental variable Z should be 0. Just like how it's kind of similar to the consequence of endogeneity, or a part of aspect of endogeneity right here. So obviously we can't have a correlation with the error with our new instrumental variables. The general process will kind of go as we determine our instrumental variables, or what might potentially be our new IV variables, IV for instrumental variables. So we regress that Z onto the X. In a way, we kind of compare how different or similar X is to Z. We'll save the fitted values, so we'll save that function, and we'll use that function to regress Y on that exact values of the outcome. And so when we do that, we'll receive our new coefficients, and those new coefficients are what we can use for utilizing the standard errors, so for like hypothesis testing and stuff. So we're essentially comparing the new IV variables to X, and then also testing them on Y. And then we're seeing the impact of Z onto Y, which is our new beta. So this first example is, I didn't necessarily cover this, but kind of like a mathematical example. I just wrote it out just to make it quick, but if our estimated standard error of beta B2, our slope, is the known standard error divided by our absolute value of the correlation between our IV and our X, then given these values here, our correlation being 0.5, our beta 2 estimate being 8, and our standard error of the beta 2 being 3, what is our new 95% confidence interval? And so based on our new instrumental variable, we can kind of like recalculate the confidence interval of X, or of the coefficient. So just inputting here, our standard error being in the numerator 3, our correlation being half, that being 6, and then us creating the confidence interval because our beta 2 estimate is 8. So from 2 to 14. I think this example I gave isn't the most applicable. Can't recall why I chose this example, but um, when we're going over these concepts, definitely try to understand more intuitively rather than mathematically at this point. Mathematically, like it is important, but I think the way endogeneity works and how it's corrected for is definitely more appropriate when um, learning about these topics. All right. So just like all of the other parts of our inferences, we want a formal test on whether our instrumental variable is appropriate. And so what we will first utilize what we call the weak instrument test. It'll utilize the f statistic for the coefficient of the instrumental variable z. And if the f statistic test results in a value of greater than 10, then we conclude that it is a strong instrumental variable. If it's anything less than 10, we'll usually conclude that's a weak instrumental variable. This 10 value isn't like a cutoff of like every of all the ways we determine if it's strong or not, but I think just generally the most common value is the cutoff is 10. All right. The Wu-Hausman test, I just wrote the Hausman test. We actually went over this, but it will similar to I believe heteroscedasticity. It will extract the residuals from the regression, and then it will distinguish its fitted values, our exogenous, from its residuals being our endogenous. So this makes sense because our errors or residuals is interpreted as the endogenous because that's the part we kind of don't understand what is going wrong in our function, while our exogenous is our fitted values. So that's what we kind of can mathematically calculate on top of based on like a systematic some minimization of sum of squared errors we do to distinguish us from our unknown part of the error. Our null for this Hausman test is that the the delta, I believe this is a slope, is simply just zero, which will result in the correlation of the instrumental variable and then the x being zero. Alternative being that they're not random. And so if this is rejected, we conclude that that there is endogeneity because we if we don't want endogeneity, we don't want this to be random. Or yeah, if we want endogeneity, we want the correlation of these two variables to be random. And so we still have to consider the addition of instrumental variables, saying that it may be necessary. And the reason why we say it may be necessary is because we have to go through one last test called the Sargon test. What that'll do is it'll take the residuals from the regression, it'll regress the error on the instrumental variables, similar to what we've seen before. Compute the sample size times the R squared, the goodness of fit, and then compare it to the critical value. So if it's less than the critical value, then we do not reject the null. The null saying that the IV is valid. And so if we accept the null that the IV are valid, that means there is endogeneity, while the alternative saying there is no endogeneity actually, and our model is fine. So in order for us to conclude that there's endogeneity, we must or in order for us to conclude that the instrumental variable is appropriate, it has to go through the weak instrument test, the F statistic being greater than 10, that first, and then after that, we need to go through the rejection of the null for the Hausman test, saying that the correlation is prevalent, it's not random. And then we need to be able to accept that the null hypothesis, saying that the instrumental variables are actually valid. So the different part of these two, saying that we actually don't reject the null, or we don't want to reject the null if we're trying to include the null, if we're trying to include the IV variables. Yeah. All right. In the next video, I'm going to be covering simultaneous equations. That is a part of what I've just covered about endogeneity. So make sure you go over this before you go on to the next video if you don't understand this part.